All right, 203 students, welcome to your tutorial for homework number 2. This is Scott. You'll get to know me in the TA lab if you come, but hopefully this recording means you don't have to come meet me. Not that I don't want to meet you, that's just kind of Dr. Scott's philosophy on the class. But please do feel free to come visit me if you have questions. We're not discouraging you, this is just an extra help. But we're going to start with problem 1.6-4. As you can see on your screen, we have a stress-strain curve for a certain metal. I think it's tungsten, didn't write it down. And we are going to load this metal beyond its yield point and see what happens. So it says that we load it to a strain of 6 millimeters, which would be considered E sub B in this case. And you can see in line 1 that E sub B is going to be the change in length over the length, or delta over L, which is 6 millimeters over 750 millimeters, which is 0.008. So that means that on our stress strain curve, we follow the curve all the way until it reaches 0.008, which is the dot at the top of the curve. Then we release the piece of metal. And when we release it, it's going to have something called an elastic recovery, or it's going to follow the slope of the elastic region, or the linear region at the beginning, all the way back down until the stress is 0. So you can see that I've drawn a line that is parallel to the initial line that ends at 0.001 and 28 megapascals, and it follows that down until it gets to 0. At that point, we have our permanent set, or our permanent strain. And you can see in line 2 that I estimated that to be about 0.0057. If you just look at the graph, it's a little less than 0.006. So then the permanent set in line 3, delta perm, is going to be the initial length times the elastic recovery, and we get that from our simple strain equation, which is epsilon equals delta over L. If we solve for delta, we get this equation in line 3, and by plugging in our numbers, we find that the permanent set is 4.28 millimeters. So this bar, after we've stretched it and let go, is going to be 4.28 millimeters longer than it used to be, because we stretched it beyond the elastic limit. Is basically the idea here. Then in part B, it asks us what the new proportional limit is going to be if we try to strain this bar again. Now the proportional limit, proportional means linear, means that the region, or how much stress we can put on this bar, and the stress strain curve will be linear. So at the beginning, the proportional limit was only 28 megapascals. As you can see, after 28 megapascals, it's no longer linear, it starts to curve. But now our bar is going to follow the same path up that it took down when we released it and it had some elastic recovery. So the new the new proportional limit is 65 megapascals, which was what equated to our strain of 0.008. Because the bar is starting at the bottom of that big long straight line, and it's going to go, if we stress it, all the way up to the big dot at 65 megapascals before it starts on that curved line again. So by stretching this beyond its proportional limit, we actually increased its proportional limit, which is an interesting thought. The book gives 65.6 megapascals, but the graph isn't that clear. So if you're around 65, it's just by inspection, then you're good. Okay, moving on to problem number 2, which is 1.7-1. We have another bar, and this time it is being compressed, and it's used in a crane, and because of the way it's built, there's a limit on how wide this bar can get. It starts with a diameter of 2, and the diameter can't end up being more than 2.001, which means the change in diameter, as you can see in the box on the right, has to be at maximum 0.001. I've also got the information on the bar over there, like the modulus of elasticity and Poisson's ratio, which we're going to need later. So in line 1, we start with the definition of the lateral strain. Now this strain has a prime on it, epsilon prime, because it is perpendicular to the direction of the loading, or the P forces. So epsilon, just epsilon, is in the same direction as the forces. Epsilon prime is perpendicular to the forces. So that's why it's related to the diameter, because the diameter is perpendicular to the forces. So line 1, epsilon prime, is the change in diameter over the initial diameter, just like epsilon was the change in length over the initial length. And plugging in our values, we get that epsilon prime has to be at maximum 0.0005. In line 2, we use the definition of Poisson's ratio, which is nu, or the V symbol, is negative epsilon prime over epsilon. We know epsilon prime and we know Poisson's ratio, which means we want to solve for epsilon. And by doing that, plugging in the numbers, we get that epsilon is minus 0.00172. Now that minus sign just means that it's getting shorter, which makes sense because the bar is being compressed. So I am going to ignore the minus sign from now on because I know in my head that it just means it's getting shorter. However, if you keep the minus sign, that's okay. It could make things a little more clear for you. In line 3, we use our definition of stress strain, in Young's modulus. This is Hooke's law, which says that the stress is equal to Young's modulus times the strain. We have Young's modulus E and strain epsilon, so we plug those in to find that the stress this bar is feeling is about 50 KSI, which stands for kilopounds per square inch, or 1,000 pounds per square inch. And then in the last line, the definition of stress is a force over an area. We know stress, we know area because we know the diameter, so we just want to find the load P, or the force, which is the same thing. And so solving for P, we find that P was 157 kips, which stands for kilopounds, or 1,000 pounds. And it's as simple as that. Moving on to the third and final problem, we have once again a bar, this time made of Monel metal, which is an alloy, being pulled, and we are told the change in length, or the delta, which you can see over in the box on the right, is 0.0195 inches. And from that, they want us to find the change in diameter as well as the force that's being applied. So for the change in diameter, we need to start with finding epsilon in the strain direction, in the pulling direction. So that's going to be in line 1, epsilon equals delta over L, and plugging in numbers, we find epsilon, which is about 0.002. Then using our definition of Poisson's ratio, we can find the strain in the lateral direction, or in the perpendicular direction. And that's important because we care about the change in the diameter, which is related to epsilon prime. So we plug in our numbers. In line 2, I forgot to label it, sorry about that, and we find epsilon prime is about 0.00069 negative, because if it gets longer, that means that the diameter has to get smaller. Then we use our definition of epsilon prime, delta over D, plug in the numbers that we know, and we find that change in D, which is what we wanted from the beginning, is negative 1.65 times 10 to the minus 4 inches in the box there. And this means, the minus sign just means that the diameter is getting smaller, so that's okay. And that's what they asked for. So then the other thing they asked for was the load, P, and we're going to use a similar strategy to the last problem where we say that stress, sigma, is P over A, And we also know that stress sigma is E times epsilon. So we don't know stress, but we do know E, epsilon, and A, which means that we can combine those two equations, as you can see in the next line, and say that P, the load, is equal to E times epsilon times A. And then if we plug in numbers for those, we find that the load P was 2.15 kips, or 1,000 pounds. Quick note, like it said in the problem, we had to look up the properties of Monell from table I2. That's where we found E and nu, or Poisson's ratio, for this metal. Thanks guys, good luck. Come see us in the TA lab if you have more questions. I hope these videos are helpful. See ya.